Hello all, this is Valentino. Welcome to my channel. In this video, we will go over an international GCSE physics paper, and specifically the paper 1P from November 2024. So it's kind of recent, about 2 years ago. In my A-level videos, I usually say a few things before we start the papers, and I'm gonna say the similar things here. So for this test, you have 2 hours, which is 120 minutes, okay? And there are 110 marks in the paper, which means that you have to budget about a minute per mark. What I mean by that is that if a question awards 10 marks, it should take you about 10 minutes, okay? So it's good to keep track of time so you score maximum marks and you have enough time to finish all the problems, okay? That's the first thing. The second thing is that what I always say is that half the answer is in the question, which means that if you understand the question, if you read the question thoroughly and you make sure you understand it perfectly, then you stand higher chances of answering the question correctly, okay? The third thing is that don't lose momentum trying to work on problems that do not occur to you immediately. So if something's complicated and it doesn't come to you, etc., skip the question because it's better to build momentum and confidence by working on the problems you know how to solve. Okay, and once you are done with everything that you do know how to deal with, you can return to the questions that gave you trouble in the end. Okay. The fourth thing is that often it's good to check the formulas that they give you. So there are some formula in the beginning of the paper and some at the end. So once you return to those questions that gave you trouble on a first read, you can skim through all these formulas and try to find something that might help you to deal with a problem. Okay, and the last thing, I think I covered everything I wanted to say. But the last thing is that questions come. Oops, I wrote there by accident. So questions come with multiple parts. So, for example, question 1 has a part A, B, C, D, etc. So if part A doesn't make sense, for example, in any question, okay, skip it and try to read part B. Sometimes you might be able to deal with part B, or maybe part B will guide you in what part A is actually asking you to do. So try to read through the questions carefully, which takes us back to the first thing I said, no, the second thing I said, which was half the answer is in the question, okay? So these are general strategies, you can follow with any tests you might do. I mean, in other subjects, when you move on to your A levels, university, even graduate school, even life, okay? So it's good to understand. Communication is key. It's good to understand what you have to do in any situation. So, question 1. Diagram 1 shows a planet orbiting a star and a moon orbiting a planet. Question A. On diagram 1, draw the orbit of a comet around the star. So I'm going to use orange. So a comet looks like this. So it's an elliptical orbit. So I'm going to try to do a good job. So something like this would be a comet. Okay. So an ellipse. Okay, maybe we can move it there. Okay. So a comet is an ellipse with the star as one of its foci. So there would be the second focal point of the ellipse, for example. Okay, and I mean, this is a correct solution as well. I mean, it's still an ellipse with one focal point being the star. Okay, so okay, maybe I should write this down for reference. So ellipse. So actually, let's write elliptical orbit with star as one of focal points. Okay, so I just saw my handwriting and I thought internally that I have to improve it because I receive a lot of negative comments about it, but I hope my explanations are understandable anyway. Okay, B, part 1. On diagram 1, draw an arrow to show the force the planet exerts on the moon. Let's take the... Okay, let's move the orbit of the comet a little bit because... oops, what did I do? Anyway, I'm not gonna move the orbit because I don't know how to do it, but this is the force. Okay, so there is a force F pointing towards the planet. Okay, so that's the force the planet exerts on the moon. Okay, and that force is what forces the moon to undergo a circular orbit around the planet. Okay, part 2. What type of force does the planet exert on the moon? It's a gravitational force, right? I mean, the other ones don't make any sense, so I don't think it's worth commenting on that. So let's move on. Part C. The planet completes one orbit of the star in a time of 2.5 times 10 to the 8 seconds. The radius of the planet's orbit is 8.7 times 10 to the 10 meters. Calculate the orbital speed of the planet. Give your answer to two significant figures. Because I never taught at the GCSE level in an actual classroom, at least. Okay, this is what I wanted to check. So they give you actually this formula over here. So this is what we will use. So let's go back over here. So V is 2 pi R over the period. So let's draw a line. So 2 pi times 8.7 times 10 to the 10. And I put the units separately to the right after the numbers, okay? Over 2.5 times 10 to the 8 seconds, okay? And this gives you 2,186.54, which we will write as 2.2 times 10 to the third meters per second. Okay, D. Diagram 2 shows the region around the sun, a yellow star, where liquid water can exist on the surface of planets. This is because the surface temperature of the planet is between 0 and 100 degrees Celsius. Okay. Explain what would happen to the position of the liquid water region if the sun was replaced with a blue star of the same size. So a blue star has a much higher surface temperature. So Earth or any planet has to move way outside, so further away from the star. So maybe, I don't know, over here, okay? And so that the surface temperature is constant. By the way, the surface temperature does not only depend on the distance from the star, but also on the atmosphere. So, I mean, this is a very simplified picture for those of you who are interested in physics. So the region around a star, any star, where water can exist in its liquid phase, it is called the Goldilocks zone. And I think Goldilocks is something that they took out from a fairy tale, but don't quote me on that. Double check. So anyway, so let's write this down. A blue star is hotter than a yellow star. Okay. Since the surface temperature, okay, needs to stay between 0 and 100 degrees, 0 and 100 degrees Celsius for liquid water. And I'm going to use a clean page, okay, for liquid water, okay. The temperature zone, okay, needs to be pushed out, okay. So the liquid water region is further out. So region is further out from the star. Okay, so that's the answer. This was problem 1. Let's move on to problem number 2. Question 2, an athlete jumps vertically from the ground. The athlete has a mass of 85 kilograms, like me. I weigh exactly 85 kilograms and I'm 1 meter and 85 centimeters tall. So full symmetry, okay? So the athlete has a mass of 85 kilograms and leaves the ground with an upwards velocity of 4.5 meters per second. State the formula linking kinetic energy, mass, and speed. So kinetic energy is 1/2 times mass times velocity squared. Okay. Calculate the athlete's kinetic energy at a speed of 4.5 meters per second. So the kinetic energy is going to be 1/2 times 85 times 4.5 squared. So that's 860.63, which you can approximate as 860 joules. Okay, 3. At the maximum height of the jump, the athlete has a speed of 0 meters per second. Okay, makes sense because all the kinetic energy converts to gravitational potential energy. Okay, state the increase in the amount of energy in the athlete's gravitational potential energy store from the ground to the maximum height of the jump. So as I just said, on the ground there is only kinetic energy, but once the athlete makes it to the top, the kinetic energy is 0 because he or she has 0 speed. Therefore, all the kinetic energy converts to gravitational potential energy. So 860 is the answer, okay, which is the kinetic energy converted to potential energy. 4. State the formula linking gravitational potential energy, mass, gravitational field strength, and height. So GPE is mass times the gravitational field strength times height. Calculate the maximum height of the athlete's jump. So mgh is GPE, which means that h is GPE over m times g. So we get 860, and I'm going to use the exact value, 0.63 over 85 times 9.81. This yields 1.03 meters, which we approximate as 1 meter. Okay. B. Sketch a velocity time graph for the athlete's jump from the ground to the maximum height of the jump. No numbers are required. Assume there is no air resistance. Okay, at this level, I'm not sure you learn about Suvat equations. Let me quickly check before I tell you. So this is a Suvat equation, for example, the one I'm underlining right now, but it's not useful to us. Let me go to the back of the paper. I want to check something before I tell you the answer. So there's a mathematical way to describe the answer, and then no, they don't. So this is something that you don't learn yet. Okay, so let's do it qualitatively then. So at time 0, the athlete has maximum speed, right? And at some time later, once he or she makes it to the maximum height, the speed is 0. Okay, so it's a straight line that connects these 2 points. Oops. So that. Okay, so that's the answer. Okay. Without equations, I don't know how else to explain it. So yes, maximum velocity at the beginning, and then the athlete decelerates with constant acceleration as they go. Constant deceleration as they go up, and that deceleration is equal to g, pretty much. Okay. So part 2, what feature of the velocity time graph gives the acceleration due to gravity? That's the gradient of this graph. Okay, because the gradient is velocity over time, which is acceleration. Okay, so 3, explain why the gravitational field strength on the moon is different from the gravitational field strength on the Earth. So the moon has a smaller mass than the Earth. Okay, G depends on the mass. Actually, G is proportional to the mass. Okay, so a smaller mass leads to a smaller G. Okay, and also a third point, also G is proportional to 1 over R squared. You probably don't learn this at the GCSE level. So the moon is smaller, different radius, so different G, okay? So different R between Earth and moon. Okay, so this was question 2. Let's move on to question number 3. Photograph 1 shows a power supply for some electrical equipment. The electrical equipment is connected to the mains supply. Explain why the power supply is completely covered in plastic. So the plastic acts as an insulator. So acts as an electrical insulator. Okay, so that's that, I guess. So it stops current from reaching anyone touching it. Okay, it will be dangerous. All right. B, the electrical equipment is connected to the mains power supply of 230 volts. By the way, it's the same voltage supply as in Cyprus. State the formula linking power, current, and voltage. That will be power is current times voltage. The electrical equipment has a power of 350 watts. Calculate the current in the equipment when it is being used. So I is power over voltage. So 350 over 230, which yields 1.52 amps. Okay, let's move on. Part C, photograph 2 shows a circuit breaker. Explain the advantages of using a circuit breaker rather than a fuse. So a circuit breaker, okay, reacts faster, okay, than a fuse, cutting the circuit off more quickly after a fault. Okay, a circuit breaker, okay, can be reset and used again, okay, while a fuse, okay, needs to be replaced once blown. Okay, so this was question 3. Let's move on to question number 4. Okay, question 4. A teacher investigates a sample of radioactive material. The graph shows their results. Okay, question A, on the graph, give the unit for activity. That's becquerel. Okay, so I'm going to write it in full. So becquerel, just for the history of it, was a French scientist who observed that some rocks containing uranium at the time, they didn't know about it yet, were emitting radiation. Okay, and I think this was discovered because by accident they had some photographic plate at the time. Photographic plates were really were something that was used to make photographs back in the day, okay, before digital cameras existed. So this material was very sensitive to light or any kind of radiation. So I think they observed that photographic plates darkened for no reason in the presence of these rocks that they had there sitting there by accident or by chance. Don't quote me on that, double check, but Becquerel was indeed a French scientist. I think he lived in the late 19th and early 20th century. So let's move on. B, describe what is meant by the term background radiation. So that's radiation that is around us, okay, at all times, natural or man-made. Okay, let's write down some examples. So cosmic rays from sun or galaxy, radon gas, so that's an A, okay, rocks, medical equipment, etc. Okay, so there are many sources of radiation. Okay, describe what is meant by the term half-life. Half-life is the time taken for half the nuclei to decay in a radioactive sample. Okay, and half-life also, I'm gonna write it here, also applies to activity and mass. Okay, let's move on. Use the graph to determine the half-life of these radioactive samples. So we're gonna find the time, the activity at time 0. Okay, so at time 0, the activity is 1200. So we need to find the time. So the activity drops to 600, which is a half at this time over there, which is every little box in the x direction is half a minute, right? So yes, so that's 19 minutes. Okay, because this little box is 0.5 minutes. Okay, so 19 minutes because at time equal to 0, the activity is 1200 becquerel. So at time equal to 19 minutes, the activity is 600 becquerel. Okay, D. The teacher suggests that this formula shows the relationship between activity and time taken. So activity times time taken is a constant. Use data from the graph to determine if this relationship is correct. I can immediately tell you that it's not correct because that only applies to linear relationships, and this is not a linear graph. But okay, let's verify it. So let's erase that. So we are going to take multiple readings. So for example, the activity at 5 minutes is 1000 becquerels. So 1000 times 5 yields 5000. Now let's take another pair. So at 10 minutes, the activity is 840. This is because every little box in the y direction corresponds to 20 becquerels of activity. So 840 times 10 minutes yields 8400. We can take a third measurement just because. So at 15 minutes, the activity is 700. So 700 times 15 yields 10,500. So so the product is not a constant. Okay, so teacher was drunk. I meant wrong. Okay, so let's move on to question number 5. Okay, question 5, diagram 1 shows two magnetic poles. Draw 3 field lines on diagram 1 to show the uniform magnetic field in the shaded region between the two poles. Okay, I'm gonna use, let's keep it black, it's okay. So the field lines go from north to south pole. So that's one line, that's a second line, and that's a third line. They have to be equally spaced, meaning that this distance should be equal to this distance, but okay. So that was question A. B, diagram 2 shows a current carrying wire in the uniform magnetic field between the two poles of a magnet. The arrow on the wire shows the direction of current. Draw another arrow on diagram 2 to show the direction of the force on the wire. So I don't know if you learn about this, but this is where you apply Fleming's left hand rule, which tells you that you put your index in the direction of the magnetic field B, your middle finger, and we are talking about your left hand, okay? Middle finger should be the current, and then your thumb should be the force. In this case, B goes from north to south, so it looks like this, okay? So that's B. Then the current is perpendicular to B, okay? So that angle is 90 degrees, and it points inwards. So if I put my finger in the direction of B, and then I will have to turn my hand around in a very strange way so that my middle finger points in the direction of I, and then my thumb points straight down. That's not straight down. Okay, that's better. Okay, so that's the force. Okay, draw another arrow on diagram 2 to show the direction of the force on the wire. So that's your force pointing down. Okay, moving on. Part C, diagram 3 shows a rectangular loop of wire carrying a current in a uniform magnetic field. Explain why the loop starts to turn but stops when the loop is vertical. So there is a current again that goes around. So, okay, first of all, the direction of B is the same as before. Okay, so that's the B. And then there is a current that goes this way on the side DC, so that's I. And then on the side AB, it comes on the other side like that. Okay, let me fix things a little bit. So that's, oops, that's the current, and that's also the current. Okay, so immediately know that there is a force. I mean, it's the same situation as this one. So on side DC, there is a force F down, and because the direction of the current is reversed on side AB, then there is another force that points up. So you have a pair of forces that will turn the coil, okay? By how much? It will turn until the two forces are aligned, okay? So you see that the two forces are not aligned, meaning that they are not on the same line, right? They have a distance from the center of the coil. But once the coil becomes vertical, you will have a force F canceling the other force F. So rotation will stop. So let's write all this in words. You can also argue that the current in the coil creates its own B, okay? So let's explain it like that. So the current in the coil creates its own B, its own magnetic field, okay? The field, this field interacts with the field of the permanent magnet, okay? This produces a pair of forces, okay, on sides AB and CD of the coil, okay? This will turn the coil until, oops, it reaches a vertical position, in which case the forces are aligned, cancel, and the coil stops turning. Okay, this was question 5. Let's move on to question number 6. Okay, a student does an investigation to determine the refractive index of a rectangular block of transparent material. The student uses this equipment in their investigation: a ray box, a rectangular transparent block, a protractor, pencil, paper, and ruler. This is the formula linking refractive index, angle of incidence, and angle of refraction. And we see the formula: the refractive index is the sine of the incident over the sine of the refractive angle. A, describe a method to determine the refractive index of the material. You may draw a diagram to help your answer. Okay, so let's draw the diagram first. Let's assume that this was a paper and you can draw a block. So that's the block, okay? So first of all, you have to create an outline around the block so that you can see what's happening. And then maybe you have a laser or something. So this is the vertical. So you can shine a laser, okay? And you will have an angle I, which will refract to some new angle, okay? That will be R. And then if I draw again the vertical, okay, so that's a vertical, then this will be I again, okay? So this will be I again. Okay, so this is the idea, okay? How are we gonna do all these things? Let me use a clean page to describe it. So place the block, that's the first step. So place the block on a sheet of paper and draw its outline, okay? Shine a ray onto the flat face of the block, okay, at the chosen angle. Okay, mark the path of the incident ray and the point where it exits the block. Okay, and what I mean by that is that since imagine that you physically have the block in front of you and the paper and all you can do is to draw this line, right? The orange line. Actually, the orange looks very similar to the red, so let me choose green. So you can track only the incident ray and the outgoing ray, okay? So these are the only two lines you can draw, and then you have to use geometry, so you can reconstruct. Once you have the outline of the block, you can then come, remove the block, and internally do the geometry and find R internally, okay? Once you remove the block. Okay, I hope this is understandable. So let's move on. Okay, remove the block, which is what I just said. Remove the block and draw the normal, okay, at the point where the ray entered, okay, at right angles to the surface, okay. Use a protractor to measure the angle of incidence and refraction, okay. Repeat for several angles, okay. For each pair of angles, find n, which is sine of I over sine of R, and then average all these values to find n, which is the index of refraction. Okay, so this was a long answer, but I hope it's clear. Let's move on. B, the refractive index of the material is 1.2. State the formula linking the refractive index and the critical angle of a material. Okay, so that will be n is 1 over sine of the critical angle. To calculate the critical angle of this material, so sine of the critical angle is 1 over 1.2, which gives you that C is 58.4 degrees. 3, describe what is meant by the term total internal reflection. So this happens, okay, when light travels, okay, from a medium with a higher n to a medium with a lower n. Okay, if the angle of incidence is greater than the critical angle, okay, all the light reflects back inside the medium. Okay, let's move on. Part C, the diagram shows a ray of light entering a prism made of the same material as the rectangular block used in the student's investigation. Use a protractor to determine the angle of incidence at the point where the ray of light is incident on side AB of the prism. So I will have to bring up the ruler, which I hate. For those of you who are following my videos, you will know that. So now we have to turn it and then, oops, sorry. So let's turn it. It says, okay, this does not help because, okay, so that's 21. And if we turn it to align with the dotted line, with the dashed line, we get 45. Okay, so 45 minus 21, that's 24 degrees. I hope this is understandable. I'm sorry I don't have a protractor. The best protractor I have is whatever GoodNotes provides. So, and GoodNotes is not sponsoring me, by the way. They should. So yes, 24 degrees. Okay, complete the path of the ray of light. Okay, they don't specify whether we have to calculate the the angle of refraction. So I'm just gonna draw a ray of light that goes like that. So it's further away from the normal because we go from an optically dense. So this is 1.2, the index of refraction is 1.2. So we go from an optically dense material to air, which has an index of refraction of 1. Okay, this was question 6. I hope this is clear. Guys, if something is not clear, write in the comments and I always reply. At least as for now, because the channel is still very young and not a lot of viewers follow. By the way, like and subscribe. 90% of the viewers are not subscribed, which is very sad. Okay, I'm trying to say that if this channel grows to 1 million viewers, I'm not gonna have time to go over all the comments, but for now I can. So, is this the reason why people doesn't subscribe? They want my channel to stay small, so I pay attention to them. Anyway, so let's move on to question number 7. Okay, now in my head, when I saw the submarine, the song "We Are All in a Yellow Submarine" plays. So, okay, the diagram shows a submarine at rest underwater. There are 2 vertical forces acting on the submarine. One of the forces is called upthrust. Give the name of the other force, that's the weight. 2. Draw 2 arrows on the diagram to represent the vertical forces acting on the submarine. So that will be the upthrust, okay, straight up, and the weight, which is down. Okay. State the formula linking pressure, density, gravitational field strength, and height. That's question B, part 1. So pressure is rho times G times H. Calculate the pressure from the water at the point 38 meters below the surface of the water. So pressure is 1030 times 38 times 9.81. That yields 383,963.4 pascals, which we will write as 384 kilopascals. Okay, moving on. C. To rise back to the surface, air is pumped into a storage tank inside the submarine. Explain how the air exerts pressure on the walls of the storage tank. So, air particles move around randomly, okay, at high speed inside the tank, okay. They constantly collide with the walls of the tank. Okay, each collision, okay, exerts a tiny force on the wall. Okay, and the total force, okay, let me use a clean page in the back, and the total force spreads over the walls area, okay, producing air pressure. Okay, part C, part 2, the air in the storage tank starts at the pressure of 410 kilopascals. As the submarine rises, the air in the storage tank increases in temperature from 2.5 degrees Celsius to 18 degrees Celsius. The volume of the storage tank remains constant. Calculate the pressure of the air in the storage tank at 18 degrees Celsius. In my solutions, I actually use the ideal gas law, which I believe you are not taught at the GCSE level. So I'm going to check the back of the paper to find the formula that you will be familiar with. So this is what I used. Since the volume is constant, pressure over temperature is constant. So we're going to use that to solve the problem. Okay. And from what I see, yes, you're not taught the ideal gas law. So that's for the A level. Okay. So we're going to use the initial pressure over the initial temperature is equal to the final pressure over the final temperature. So the final pressure is equal to the initial pressure times the final temperature over the initial temperature. So we have 410 times, don't forget to convert to kelvins, okay? Because if you use Celsius, you will get a wrong answer, okay? So 273 plus 18 over 273 plus 2.5. This yields 433 kilopascals. And this was question 7. Okay, let's move on to the next question. Question 8, the diagram shows two whales in the sea. Some species of whale communicate with sound signals and visual signals. Okay, describe the difference between the motion of particles in a transverse wave and the motion of particles in a longitudinal wave. You may use a diagram to help your answer. So let's do the transverse wave. So particles oscillate, okay, at right angles with the direction of the wave motion. So these are the particles and they move like that, up and down. Okay, longitudinal waves, particles vibrate parallel to the direction of motion. So particles vibrate parallel to the direction of motion. Okay, so these are the particles and they move in this direction as the wave moves to the right. Okay, so let's move on. Part B, whale A makes a sound with a constant frequency. This sound is detected by whale B. When whale A swims towards whale B, the frequency of the sound detected by whale B increases. This is known as the Doppler effect. Explain how the Doppler effect causes the frequency of sound detected by whale B to increase. So as whale A moves towards whale B, okay, the sound wavefront, okay, gets squashed. Actually, let's write wavefronts get squashed closer together, okay, in front of it, meaning lambda gets shorter, the wavelength. So what's going on is that as the whale moves to the right, the waves kind of get squashed, okay? And I mean, if you move away, I mean, if the whale is moving away, the wave fronts get farther away, but that's not what we care about. Okay, so let's continue. The speed of sound in water does not change. Okay, since the frequency is velocity over the wavelength, a shorter lambda, okay, means a higher frequency. Okay, so whale B detects a higher frequency as whale A approaches. Okay, part C, visible light from the sun reaches whale B. The wavelength of this light is 5.4 times 10 to the minus 7 meters. Calculate the frequency of this light. So C, the speed of light, is lambda times the frequency. So frequency is C over lambda. So that's 3 times 10 to the 8 over 5.4 times 10 to the minus 7. So that's 5.6 times 10 to the 14 hertz. All right, so this was question 8. Let's move on to question number 9. Okay, question 9. A student investigates different electrical components. Part A. The student first investigates how the voltage of a diode affects the current in the diode. They use this equipment: a diode, a cell, variable resistor, wires, voltmeter, and an ammeter. Draw a circuit diagram to represent a circuit the student could use. The diode has been drawn for you. So we will need a variable resistor. Okay, we will need a power supply. Okay, so that's the power supply, the potential difference. Okay, we will need an ammeter to measure the current. We will need to complete the circuit, of course, and we will need a voltmeter to measure the voltage across the diode. Okay, and this is connected correctly as the current flows in this direction, right? So it can go through the diode, because if it flows in this direction, nothing goes through. Okay, let's move on. B. In the second investigation, the student uses a circuit with two different resistors, A and B, and a battery with a voltage of 2.9 volts. Diagram 1 shows the circuit and the current in each resistor. Calculate the current in the battery. So we have to add up those two pretty much. So 0.15 plus 0.23, 0.38 amps. 2. State the formula linking voltage, current, and resistance. Okay, so voltage is current times resistance. Calculate the resistance of resistor A. So R is 2.9 over 0.15, which is the current that goes through resistor A. Both resistors have the same potential difference across them because they are connected in parallel. So that's 19.3 ohms. Okay, moving on. 4. Diagram 2 shows the same three components connected in a different circuit, so they are in series now. Okay, resistor B has a resistance of 13 ohms. Comment on the difference between the current in the battery in diagram 2 and the current in the battery in diagram 1. Use calculations to support your answer. In diagram 2, okay, A and B are in series, so resistance adds up. Okay, so R total is therefore 19.3 plus, let's call it 19 there, okay? So 19, plus 13, so 32 ohms, which is larger than both RA and RB. Okay, now the current is going to be V over the total resistance, so 2.9 over 32, so 0.09 amps, which is less than 0.38 amps in diagram 1. Okay, so series resistors is the conclusion. Always have higher resistance and lower current than when they are in parallel. Okay, so I think this is a complete answer. We are ready to move on to question number 10. Okay, this is a strange arrangement. I've never saw this thing before in my life. So, 10. A student investigates energy transfer by conduction in different metals. The student uses wax to attach one coin to each of 4 different metal rods and connects the rods to a heater. Okay, so we see this from the top. When the heater is on, energy is transferred through the metal rods. This melts the wax and causes the coins to fall. So heat transfers this way. Okay. The diagram shows the student's equipment viewed from above. Okay. Question A. This is the student's method. Step 1, switch on the heater and start a stopwatch. Step 2, record the time taken for the coin to fall from each metal rod. Question I. Give the independent variable in this investigation. That will be the type of metal. Type of metal. Okay. To give the dependent variable in this investigation, this will be the total time. So time taken for the coin to fall. All right. Question 3. A teacher tells the student that their investigation is not valid. It's not a fair test. Give 2 ways to improve the validity of the student's investigation. So rods must have the same length and diameter, because as you can see, they have different lengths. So aluminum is longer, iron is thicker, etc. So it's better to have the same length and diameter to have, so that the test is fair. And you have to use the same amount of wax and the same coins for all metals. Okay, part 4. The student improves the validity of their investigation. Describe what the student should do to improve the reliability of their results. So repeat the experiment for each metal rod and calculate the mean time. Will improve reliability. So let's write it down. Repeat the experiment multiple times and calculate the mean time for each rod. Okay, let's move on. Part B, the table gives the students' results. Plot a chart of the results on the grid. Okay, so we're gonna take each square to represent, let me think, 50 seconds. So let me think. So that will be 25. So 5, 10. Okay, so each small square is 5 seconds. Okay, each little square in the y direction. Okay, so let's start with the smaller one, copper. So 90 will be this box. So this is iron. Oh, sorry, copper. Okay, the next one is aluminum, 140. So we need 2 large boxes, so 50, 100, and then 140 is that one. Okay, hope I don't run out of space, by the way. Oops, there, and then there. So, by the way, I will have to move them a little bit. So let's move this. Let's move it there. Okay, let's also move this there. Okay, that looks good. let's erase that. So this is aluminum. Okay, the next one is iron, 180. So we need 3 large boxes and then some. So that will be okay. Okay, there. Okay. I hope you guys are following. Okay, that will be what is this? Iron. And the last one is steel, so we need 230. So we need 4 large box and then some. Okay, so this is steel. Okay, state why a bar chart is a better choice than a line graph for this investigation. So material is a categorical variable. Okay, not a continuous variable. So it doesn't make sense. I mean, if you draw a line connecting these boxes, it doesn't represent anything physical. So that's the answer. Okay, and let's move on to the next and last question in this test. Okay, question 11. Which of these is the main source of energy in stars? That would be nuclear fusion. Okay. Alpha decay and beta decay make no sense. Nuclear fusion does not happen in stars because you need heavy metals. In stars, you have light metals. Yes, astrophysicists call anything heavier than helium a metal, I believe, or maybe lithium. So check it out. Okay, B. The table lists the stages of development of a star that has a very much larger mass than the Sun. Give the stages in the correct order using numbers 1 to 5. So a black hole is formed. That would be the last stage, but let's see the other options. Heavy elements are made in the core of the star. The star becomes a red supergiant. The star explodes. The core of the star. Okay, so this represents the late stages of a giant blue star. Okay, so first it runs out of hydrogen in its core, so that would be 1. Okay, it then turns into a red supergiant, so that would be stage 2. In that stage of a red supergiant, heavy elements are made in the core of the star. Okay, that will be stage 3. Eventually, it keeps building pressure and energy, so this leads to a supernova explosion, which will be stage 4. And as I said in the beginning, the black hole stage is the last stage, so that will be 5. Okay, and this was paper 1P from November 2024 for the GCSE levels. Okay, in this channel, as I say multiple times, the channel started out of my frustrations with life and being unemployed currently and stuff like that. The main goal was to discuss physics, okay? The main goal is to discuss physics, but gradually I started developing an appetite for anything and everything, okay, related to things I like. So recently I even uploaded a video that is kind of like documentary style about the medieval history of Cyprus if you want to check it out. But I'm trying to say that as the channel evolved, I ended up uploading many past papers related to the A-level physics. And then one time I posted the GCSE paper just for a change, and I saw lots of viewers watching the video. So that became a thing that I started uploading. So GCSE level physics. I also uploaded mechanics A-level tests. I even uploaded a physics research paper, and I discussed how you can reproduce it. So I'm keep working on the channel. It was recently monetized. I'm not rich though. I don't make anything from the channel yet, and to make anything from YouTube ads, you need to have millions of subscribers. So yeah, I'm not there yet, and I don't know if I will ever make it there. So anyway, the bottom line is that I hope these videos are useful. Let me know what you think. Tell your friends, share the videos. Please subscribe so the channel grows. If you have many subscribers, YouTube promotes your channel, and so on and so forth. So see you guys in the next videos.